In this video, we're going to learn how to solve rational inequalities. This will be very similar to what we did in our previous video, except now we'll have inequalities involving rational expressions. Let's work through some examples. In our first example here, we want to solve the inequality x squared minus x minus 6 over x minus 1 is less than or equal to 0. This is a rational inequality because we noticed on the left-hand side here, we have a rational expression. Our procedure for solving these inequalities will be the same as when we solved polynomial inequalities. Our first step is to move everything to one side and call the resulting function f of x. In this example, everything is already on one side of the inequality, and we have 0 on the other side. So what we have on the left-hand side here, this is what we'll call our function f of x. So to find the solutions for this inequality, we're essentially asking ourselves, for which x values is our function f of x less than or equal to 0? Or in other words, when is our function f of x negative or 0? To answer this question, we need to determine where our function is positive and negative. And to do that, we'll be making a sign chart. First, we'll need to find the x values where the function might have a sign change. In our previous video, we saw that a function might have a sign change at the x-intercepts, and a function might also have a sign change at vertical asymptotes. When we were working with polynomial inequalities, we did not have to worry about vertical asymptotes, but now that we're working with rational functions, we do need to find them. So first, let's find the x-intercepts. Remember, to find the x-intercepts, we want to set our function equal to 0 and solve for x. So here for our x-intercepts, we want to set our function x squared minus x minus 6 divided by x minus 1 equal to 0 and solve for x. To solve an equation like this, we might start by getting rid of the denominator. What we can do is multiply both sides by x minus 1. On the left-hand side, the x minus 1 will cancel out with the x minus 1 in the denominator, leaving us with just x squared minus x minus 6. And on the right-hand side, 0 times x minus 1 is still 0. So we've transformed our equation to essentially just the numerator of our rational function equals 0. And this is a shortcut we can do when we want to find x-intercepts of rational functions. Instead of setting the whole function equal to 0 and solving for x, all we have to do is set the numerator equal to 0 and solve for x. Now going back to our equation, x squared minus x minus 6 equals 0, we can solve this by factoring. We need to come up with two numbers that multiply to negative 6 and add up to negative 1. Those two numbers are negative 3 and positive 2. So the left-hand side here factors as x minus 3 times x plus 2, and this is equal to 0. Now, since we have a product of two things and it equals 0, that tells me either the first factor equals 0 or the second factor equals 0. So we can split this equation up into x minus 3 equals 0 and x plus 2 equals 0. On the left here, if we have x minus 3 equals 0, we can add 3 to both sides to get x equals 3. On the right here, x plus 2 equals 0. If we subtract 2 from both sides, we get x equals negative 2. So our two x-intercepts are x equals 3 and x equals negative 2. When we plug those x values into our function, we'll get 0 as the output. Next, let's find our vertical asymptotes. To find our vertical asymptotes, what we're going to do is set the denominator of our rational function equal to 0 and solve for x. I want to point out that normally, when we find vertical asymptotes, we have to cancel out common factors between the numerator and denominator. But here, we're skipping that step, so what we find isn't guaranteed to be vertical asymptotes. We might find holes as well. While the sign of our function won't change at a hole, it's still a good idea to find them. That way we know which x values we can't plug into the inequality to begin with. So to find our potential vertical asymptotes, what we're going to do is set the denominator, x minus 1, equal to 0, and we'll try to solve for x here. All we have to do is add 1 to both sides, and we get x equals 1. And it turns out that this is a vertical asymptote because the numerator does not have a factor of x minus 1. So now we found all the places where our function might change signs from positive to negative or negative to positive. We're ready for our last step, which is to make a sign chart for our function. To make a sign chart, we start by drawing a number line. And on our number line, we're going to place the x values where my function might change signs. We'll start with our smallest x value and then work our way up. The smallest x value is -2, so let's place -2 on our number line. Then we have x equals 1, so place 1 on our number line. And then lastly, we have x equals 3, so let's place 3 on our number line. So this divides up our x values into 4 separate intervals. And we know that throughout each of these individual intervals, the sign of our function will be consistent. So to fill out our sign chart, we're going to pick an x value in each of these intervals. We're going to plug them into our function, and we'll try to determine the sign of the output. Let's start with this leftmost interval. We're looking at x values less than -2. So for example, we can pick something like -3. We want to take -3, plug it into our function, and see what the sign is. F of -3, this is equal to -3 squared minus -3 minus 6 divided by -3 minus 1. Plugging this into our calculators, we end up with -3/2 here. And since -3/2 is a negative number, we're going to draw a minus sign on this leftmost interval on our sign chart. Next, we can move on to our second interval, the x values from -2 to 1. So pick an x value in between here. For example, we can pick x equals 0. We're going to take 0, plug it into our function, and see what the sign of the output is. So f of 0 would be 0 squared minus 0 minus 6 divided by 0 minus 1. So in the numerator, we end up with -6. In the denominator, we end up with -1. So our output is +6. And since that output is positive, we're going to draw a plus sign on this second interval. Our next interval are the x values from 1 to 3. So pick an x value in between. For example, you can pick something like 2. Take 2, plug it into the function, and see what the output is. So here f of 2 would be 2 squared minus 2 minus 6 divided by 2 minus 1. Evaluating this, we end up with -4, which is a negative number. So on this third interval, we're going to draw a minus sign on the sign chart. And then our last interval are the x values greater than 3. So pick an x value greater than 3. For example, you can choose something like 4. Take 4, plug it into your function, and see what the output is. We have 4 squared minus 4 minus 6 divided by 4 minus 1. Evaluating this, we end up with 2, which is a positive number, so we're going to draw a plus sign on that last interval of our sign chart. So remember that for this inequality, we're asking ourselves for which x values is our function f of x negative or 0. So on my sign chart, let's highlight those negative intervals. For the x values from -infinity through -2, our function is negative. And then for the x values from 1 to 3, our function is negative there as well. So the solution to our inequality is going to be the interval from -infinity to -2, and we're going to use a bracket on -2 because we want to include this x value in our solution. At -2, this is an x-intercept, which means our function is equal to 0 there. And the output being 0 is something that we want for this inequality. Next, we have the interval from 1 to 3. We're going to use a bracket on the endpoint at 3 because 3 is one of our x-intercepts, which means our function is equal to 0 there. But for 1, we're going to use a parentheses because we want to exclude x equals 1. At x equals 1, this is an x value that makes the denominator equal to 0. And so we won't be able to plug in x equals 1 into our rational inequality to begin with. So this is the solution to this rational inequality. Our procedure was essentially the same as when we solved polynomial inequalities. The only difference was we needed to find vertical asymptotes for our function. Let's try one more example. In example B here, we want to solve the inequality x minus 1 divided by x plus 2 is greater than or equal to -2. The first thing we want to do is move everything to one side. So what we'll do here is add 2 to both sides of this equation, so I move everything to the left-hand side. We end up with x minus 1 divided by x plus 2 plus another 2 is greater than or equal to 0. Now, this left-hand side is what we're going to call our function f of x, but at the moment, it doesn't quite look like a rational function. What I want to do is combine all the terms together into a single fraction. But in order to combine this plus 2 with our fraction here, we're going to need a common denominator. So to do that, we're going to multiply both the top and the bottom here by x plus 2. That way we can write the 2 as a fraction with denominator x plus 2. So let's simplify this. We have x minus 1 divided by x plus 2. When we multiply the 2 to the x plus 2, we end up with 2x plus 4 in the numerator and x plus 2 in the denominator. And all of this is greater than or equal to 0. Now that my two terms here have the same denominator, we can combine the fractions together by adding the numerators. So if we add x minus 1 and 2x plus 4 together, we'll end up with 3x plus 3 in the numerator and then x plus 2 in our denominator. And this is greater than or equal to 0. So what we have on the left here, this rational function is what we call f of x, and we want f of x to be greater than or equal to 0, which means we're looking for the x values that make our function positive or 0. To answer that question, we'll need to make a sign chart for our function. But first, we need to find the x values where the function might have a sign change. So we need to find the x-intercepts for our function and also the vertical asymptotes. To find the x-intercepts, what we're going to do is set the numerator of our function equal to 0. So 3x plus 3, set that equal to 0. We can solve this by first subtracting 3 from both sides. We end up with 3x equals negative 3. Then divide by 3, we get x equals negative 1. So when x is equal to negative 1, that's when the output of my function is 0. Next, we want to find the vertical asymptotes for this function. To do that, we set the denominator equal to 0. In this case, that's x plus 2 equals 0, and we can solve by x by just subtracting 2 from both sides. We end up with x equals negative 2. And again, x equals negative 2 is going to be a vertical asymptote for us rather than a whole because the numerator of our function does not have a factor of x plus 2. Now that we've found the x-intercept and vertical asymptote, we're ready for our last step, which is to make a sign chart for our function. So let's draw our number line. And on our number line, we're going to put down our x-intercept and vertical asymptote. We have x equals negative 1 and x equals negative 2. The smaller one goes first, so let's place negative 2, then negative 1, and this divides our number line into 3 intervals. Throughout each of these individual intervals, we know that the outputs of our function will have the same sign. So let's fill out this sign chart by picking x values that are in each of these intervals, plug them into our function, and see what the sign of the output is. The first interval here consists of x values less than negative 2. So, for example, you can pick the x value negative 3. We're going to take negative 3, plug it into our function, and see what the output is. F of negative 3 is going to be 3 times negative 3 plus 3 divided by negative 3 plus 2. Evaluating this, we end up with 6, which is a positive number. So on our sign chart, on this first interval, we're going to draw a plus sign. For our second interval, we're looking at the x values from negative 2 to negative 1. Now, there's no whole number between negative 2 and negative 1, so we'll have to go with a fraction. We can pick something like negative 1.5 or negative 3 halves. Let's plug that into our function and see what the output is. F of negative 3 halves is going to be 3 times negative 3 halves plus 3 divided by negative 3 halves plus 2. When we evaluate this, we end up with negative 3. And that's a negative number, so on my sign chart, we're going to draw a minus sign above that interval. For our last interval, we want to pick an x value that's greater than negative 1. So we can pick something like x equals 0. Take 0, plug it into the function, and see what you get. F of 0 is 3 times 0 plus 3 divided by 0 plus 2. we end up with 3 in the numerator, 2 in the denominator, so this is 3 halves. And that's a positive number, so on my sign chart, we're going to draw a plus sign above that interval. Now let's remind ourselves what we're looking for. We're looking for the x values for which f of x is positive or 0. So on our sign chart, let's highlight the positive intervals. The x values from negative infinity all the way to -2, our function's output is positive there. And also the x values from -1 to infinity, the function's outputs are positive there as well. So let's write our solution in interval notation. Our first interval is the interval from -infinity to -2. And here we're going to exclude the endpoint -2 because x equals -2 is what makes the denominator equal to 0. So it's something that we can't plug into our inequality to begin with. So in our interval notation, we're going to put a parentheses at -2. And then we have the interval from -1 to infinity. This time, -1 is something that we do want to include, so we're going to put a bracket there, since x equals -1 is one of our x-intercepts, which means our function is equal to 0 at x equals -1. And that's something that we want in our inequality. So the solution to our inequality is the interval from -infinity to -2, excluding -2, and then from -1 to infinity, including -1. So in this video, we learned how to use sign charts to help us solve rational inequalities.